And we're back, moments before the incident. Well, hi everyone, welcome back. We're here before a very, very interesting talk by Mr. Gorton. I was talking to Dan earlier. I was telling him that, look, I'm really curious about how to decrease my cloud usage bill. And I can't wait to find that out, because I have a hunch it's not just about setting some parameters. It's also about making some difficult architectural choices that I'm sometimes unwilling to make. So I can't wait to hear what Mr. Ian has to say about this, and yeah, how I can fix my issues, basically.
And it's not just about reducing it, but making the damn thing predictable.
Yes, also that.
Hi, Ian.
So, hi, Ian.
It's nice having you here. You're live. We cannot hear the sound.
Hello.
Yes,
yes.
Now we can.
Okay, great. So shall I share?
Yes, please do.
Okay.
Any minute now.
How's that?
Yes,
Perfect.
Loud and clear.
Great. Good morning, afternoon, evening, everybody. Welcome from Seattle, a damp morning in Seattle. I'm sure you're all pleased to hear that. This talks about building systems in clouds and the sort of intimate costs that exist when you actually deploy something in a cloud and then try to scale it up. So, quick overview of the talk in case you can't hang around. I'm sure most of you are now using clouds for your workloads and for your systems. And one of the reasons people use clouds and like using clouds is because they make rapid scaling possible. But of course, as you scale, you pay for the resources you use. So there's a link between cost and scale. And what I've done in this talk is I'll describe some of the effects that programming languages have on cost and scale, and also how platform tuning can save you quite considerable amounts of money if you're careful about it. So, one of the key benefits of the cloud is scalability. You can rapidly grow your resources that are deployed in the cloud to handle increased workload. And cloud providers make this relatively easy for us because they provide us with lots of nice packaged services that we can deploy with our systems. So you kind of have scalability at your fingertips, which is a really nice feature. You just go into your cloud console and deploy more resources. Obviously, you need to design your system correctly so it does scale, but that's the subject of another talk. Now, for most of us, scalability isn't the primary quality attribute we design for when we first build a system. We're really worried about just deploying useful functionality and keeping users happy. But in the lifetime of many, many systems, scalability becomes important. And this is because normally there's some sort of tipping point event. And we've seen one of these quite recently with coronavirus. I know here many websites crashed. Grocery store, supermarket store websites crashed because everybody was ordering online. State unemployment services were crashing left, right and centre. No one was getting paid. Instacart was overwhelmed because everybody was getting stuff delivered. And so many systems were exposed to be non-scalable because of this kind of event. And of course, these things happen, and it's up to you as an architect to anticipate when these kind of events may happen or design your system so it can scale when they do happen. Money, of course, is a big factor in your cloud, and as the introduction said, it's nice to get a predictable, not very large cloud bill every month. Some people spend enormous amounts of money on their cloud spend. Here's just a slide that shows you what people were spending, like Pinterest and Capital One, Adobe in 2017 and 2018. And there's many documented cases of people getting large surprises in their cloud bill when they deployed something they didn't quite realize, the settings weren't quite right, they deployed an extra service and forgot about it, and suddenly you see an extra $100,000 on your cloud bill at the end of the month. So one thing you really want to do is design your systems so they can scale, but you don't have this kind of reaction when you see the bill. So scalability is an interesting issue when you dig deeply into it. What you really want is for your system to be designed so it can scale exponentially. So as the workload grows, your resources can handle an exponential growth in load. But at the same time, you want to make sure that you don't experience an exponential growth in cost, because that would be really bad and you'd be like the panda on the previous slide. You really want your costs to grow linearly or reasonably slowly. And there's many strategies to do this, again, about optimization and adding resources to your system in a controlled way that we could talk about. But again, this isn't really the topic of this talk. What we call these systems that can grow exponentially, but the cost scale linearly, are hyperscalable systems. It means we can keep growing our load forever and ever, and our costs are still manageable and predictable. And as I'm sure you can imagine, this involves trade-offs. As an architect, you're constantly involved in trade-offs between deploying highly scalable functional infrastructure for your microservices, but also balancing it with the costs that you spend to support that infrastructure. And so there's a myriad of decisions that you have to make as an architect when you move to the cloud. They're not just all about the sorts of issues that Mark was talking about previously. That's part of it, obviously, but there are other issues. So do you use reserved instances versus on-demand instances? What machine capacity do you need, or how do you configure your serverless architecture so that it has sufficient memory and CPU available? Do you use cloud-hosted databases? If so, how do you handle the read-write loads? Because you typically pay on something like DynamoDB by the read and write unit. So you need to optimize your database access because it affects the costs that you see. Also, database consistency. If in many cloud hosted databases you're happy with an inconsistent data at any particular time, it's cheaper than making strongly consistent updates. So all of these issues factor into the cost, and these are many, many more, factor into the cost that you need to think about when you deploy in a cloud. Now, what's kind of interesting is, how do we do this nowadays? Well, this is the Google Cloud Platform Price Estimator. It's a fun bit of technology, but it's kind of primitive, and it's very static, and it's just gives you a vague sort of finger in the air, which way's the wind blowing type cost estimate for your systems. So about a year ago, I was talking with some architects around Seattle, and we thought, could we do better than this? And so we came up with an experiment whereby we built a system on Google Cloud Platform right now. We're hoping to move it to AWS pretty soon. And the system just had a workload. I won't go into the details of the system itself, but it's basically just supports a RESTful interface. And we mostly do post requests on this. So it's a write-heavy workload. Writes are always much more interesting to handle than reads from a performance measurement perspective, because they're much more stressful on the system. So we have a client which generates this workload. We implemented the server in 4 different languages, which are supported by the Google Cloud App Engine. So Python, Go, Java, and Node. And we then built the data model on the Google Cloud Platform hosted database Data Store, which has changed its name since then, but it was Data Store when we used it. And we thought, what happens if we keep the workload exactly the same and just vary the back-end implementation by programming language? The data store is exactly the same, so the I/O is exactly the same. The requests coming from the clients are exactly the same. We've just re-implemented the business logic, which is pretty simple in this application, in 4 different languages. So what happens? So the experiment has a given workload, which I'll show you in a second. We deployed it on Google App Engine. They're B1 instances, so they're pretty much the default instance you get when you deploy some code onto Google App Engine. And we use all the default auto-scaling settings that you get with a serverless platform. And I'll go into these in a lot more detail in a little while, but basically this was a default implementation, a default deployment. So this is what our workload looks like. You can see here that it goes through a fairly traditional sort of performance load testing profile. We have a warm-up phase where we start just by firing off a very low load of requests from the client, and this just warms up caches and warms up instances in Google App Engine. And then we scale up the workload. So we jump from, I can't remember the exact numbers, I think it gets to about 256 clients here. And then once that has more or less stabilized, we go to a peak load of 1,024 client threads, just sending requests constantly, no delay. So this generates a considerable workload. And here you can see in this particular screenshot, we were processing around 8,500 requests a second on our workload. And then we just scale it down, so we just lose resources. So in this instance, the serverless platform should be shedding resources as it sees the requests coming from the client diminishing. And so again, you'd want it to shed resources because this saves you costs. And the way the serverless platform works is you get billed by the number of instance hours that your server instances are deployed. So the sooner you can scale down, the sooner these will be removed from memory and then from billing. So we did this experiment with 4 different programming languages. And you can see on the slide here, we start off with 128 client threads, so quite a light load, and we grow it to 1,024. And the blue bar is the overall test, so that includes all the phases. And the other bar is the peak phase. So this is when we were just loading it very heavily with 1,024 clients. And so you can see the throughputs are kind of interesting. Go has a peak here of about 12,000, 13,000 requests per second. Node is more like 1,000, as is Java, and Python's a little bit slower. So let's do a bit more of a direct comparison. It's a peak load, so just during that peak phase, where most of the requests are sent, you see that in reality Go is performing considerably faster than Node, Python. Node and Java, very little in it, and Python reasonably slower compared to the others. So this is just programming language. So we see the performance differences, but what about cost? So we're interested in seeing how scaling of our infrastructure using Google App Engine and different languages affects cost. It's not just about satisfying the client requests. So this is where it gets more interesting. We see here that for those tests, the instance hours that we were billed for each of those tests for Go was around 17 instance hours, whereas Python at peak was about 50. Pretty much 3 times the cost. So Python was 3 times more than our Go infrastructure, and it actually delivered less throughput. Java and Node kind of in the middle. Java using less instance hours. Node actually, because Node is single threaded, it deploys more Node server instances into Google App Engine, hence you pay more. So if we then look at this from a price performance ratio perspective, so just a slight bit of mathematics in the background, we can see that for our dollar cost, we're getting a lot of requests per second from Go, over 10,000 per dollar. Whereas in Python, we're getting 2,500, 3,000, and Node and Java again, somewhere in between. So price performance ratio Go is looking pretty good, but the main point of this chart is it emphasizes the differences that programming language will make to your scalability and costs. So a very architectural decision, which programming language do you use when you have a choice, of course. And then if we just normalize this, we see that basically you get, for Go, you're getting 4 times, or you're reducing the costs 4 times to deliver the same workload as a Python server. So you pay 4 times less than Python if you deploy this application using Go under a heavily scaled workload. we all thought that was kind of interesting. I was actually surprised that programming language made that much difference. And Go is obviously an optimized language for Google's cloud platform because they invent the language, they manage the language. But it just shows that just choosing the programming language is a really important factor in the scalability of your system and also the amount of money you pay for that particular deployment. Now, the interesting one, or more interesting one from my perspective, was the auto-scaling parameters. So whenever you deploy on a serverless architecture, or even if you're just deploying your own containers, you're still configuring Tomcat or whatever that you're using to handle requests. And most people go with default parameter settings. And in Google App Engine, these are the default settings that you get. There's a few more of these which I've not covered on this slide because it gets complicated. This is complicated enough. So when you deploy on Google App Engine will auto-scale your code. So it will add more resources. By default, if the CPU usage of a deployed instance goes above 0.6, it will also only allow up to 10 concurrent requests in any particular instance. And this can actually be controlled by this value, the target throughput utilization, which is actually this value here is a percentage of this value. See, it's getting complicated. These are all totally interdependent. You can also configure how long requests wait for wait in a queue to be handled. Oops, sorry. So again, this is 30 milliseconds by default, and then minimum pending latency is related to this. I won't go into the details. Again, it's all a little bit confusing. But the key issue here is that most people, we talk to Google Cloud architects, the Google Cloud headquarters is actually about 3 blocks from where I work now. And most people go with these default settings. They never explore what difference it makes. And a CPU utilization of 60% before you spawn another instance, maybe it's a bit low, who knows? 10 concurrent requests per instance, maybe that's a bit low for your workload. So what we did was we designed an experiment. And these are just called parameter studies. They're actually pretty straightforward. What we do is we vary 2 of the parameters. We could vary more, it's just we only did 2 in this case to see if it was actually revealing and interesting in terms of results. So we ran a bunch of tests and filled this matrix basically with the results. So one set of tests would be the CPU utilization at default, 60%, and the maximum concurrent requests at default, 10. So we've run each test 5 times under exactly the same workload using the Go server because it was the fastest one from our programming language study. And we then just calculate the average performance that we see from about 5 different tests for each element in this matrix. So we ran a lot of tests here, as you can imagine, and there was quality checks to make sure that we didn't get any really deviant results one particular day, which you do see in clouds. I remember one Saturday morning I started running some tests and we got the weirdest results ever. Next day they went back to our stable control values. So we ran a lot of tests, and then what you can do is you can plot what's known as a response surface that shows how the performance varies across different configurations. So here you can see this would be maximum of 10 concurrent requests and CPU of 60. That would be this value here. CPU 80%, maximum current request 90. This would be this value here. And this response surface just kind of predicts the values that fall in between the points that we have actual data for. So you can see that the peak performance is somewhere around here, which is maximum of 65 concurrent requests per second, and CPU around 70. Roughly, you can see that from this particular picture. Also, just look at the peak phase. So this is when the number of client requests was at its peak of 1,024 concurrent client requests. And again, the peak phase is kind of also interesting. We're seeing peaks over here. It's a maximum of 65 and CPU utilization of 80%, maybe here. And you can see from the colors where we see a drop in performance over on this side. So of course we get at the performance, we look at the throughput and the latencies that we get, but what about the cost? So this is where for each particular test we average the amount of instance hours that we're billed for. So here you can see that the cost of the request when the maximum concurrent request was low was pretty low. Was high, sorry, compared to when we have more concurrent requests and a higher CPU utilization. We're paying considerably less. So up to about 14 instance hours here, and probably more like 6 or 7. So you can see the trends here. Again, there's kind of a peak here of value. And if you plot price performance ratio, which is always interesting, again, this is pretty obvious. You see much better price performance ratio for more concurrent requests and more CPU utilization than you do for just letting 10 concurrent requests and 60% CPU utilization. So all those are really interesting plots, but what do they mean in practice? So these are the values, the mean values from all of those tests for throughput of requests handled per second and instance hours billed. So here you can see the different configurations and the mean throughput and the mean instance hours billed. So higher performance is possible at 20% cheaper than the default settings. Where does that statement come from? Well, this is default. So this is what you get out of the box if you don't touch Google App Engine. You get 6,000 requests per second. And here's the highest performance that we see. Different configuration, we're getting more or less the same performance, a small improvement, but nothing significant. But here we're paying 11 instance hours for our test. Here we're paying 9, which is roughly 20% cheaper. So just by varying the values, we can see that we can save money. And 20% doesn't seem a lot, but if you're spending millions of dollars per month on your server deployments, then 20% is a lot of money. Another takeaway, we look at, again, the default settings that you get out of the box if you just deploy your code, and we paid 11 instance hours. The lowest instance hours for any test we see is 6. So here we're saying we're going to allow a maximum of 90 concurrent requests and a CPU load of 70. So this is nearly half the cost of this test. But what's the performance? We're paying half as much. Do we get any decent performance? Well, here we've got 6,000 requests a second, 6,006, and here we've got nearly 5,800, which is roughly 96% of the throughput for roughly 54% of the cost. So that seems a fairly significant finding, showing that if you pay attention to varying the values of your parameters on a deployment, then you can save a lot of money. And again, this is actually quite a significant value if you're spending millions of dollars per month on your cloud deployment. So paying attention to detail can really pay big dividends. How do you do this in practice? Well, there's ways to do this when you deploy on a serverless platform, which are relatively straightforward. Google App Engine, which is the one I'm most familiar with, has a traffic splitting capability. So I can deploy the same code multiple times to my App Engine deployment. I deployed as a different version with different parameter settings, and I configure GAE to send a certain percentage of traffic to each of those. So you could envision, for example, deploying each of these different deployments as a particular version and then splitting the traffic across them, monitoring the amount of cost and performance that you get, and then just closing down the ones which are expensive or slow, and then keeping alive the ones which are giving you the best price performance ratio. And that's relatively easy to do with Google App Engine and the monitoring APIs that are available. AWS Lambda has a function aliasing and traffic shifting mechanism, which is essentially exactly the same. And again, you can use Google CloudWatch metrics, AWS CloudWatch metrics, to see the difference in performance that you're getting from each particular function alias and see which one's giving you the best price performance ratio. So these are all feasible strategies to do within a cloud deployment if you want to investigate the parameter space, because all these parameters are all intimately tied together, and there's no way you can say, oh, it's got 80% CPU is going to be my best value here. You just don't know until you experiment. So really, I think the takeaway from this talk is even small optimizations when you're scaling your workload can result in major cost savings. And 10% of $1 million is quite a lot of money. It might make your boss a lot happier at the end of the month. So in summary, system scaling is a huge challenge, and most of us are now using clouds to achieve this. But clouds also cost money. And if you want to pay attention to the bills that you get at the end of the month and still achieve a scalable workload, it's worth digging in to the details of the parameter values and the programming languages that you use to deploy your systems, because you can achieve the scalable performance you need at a lot less cost. Acknowledgements for the team of folks who worked with this project with me, and I'm writing up much of this work on Medium, so if you want to follow me on there, that'd be great. Thanks, everyone.
And thank you, Ian. We also have some questions from the audience, if we may. Well, I'm gonna start reading this one. Nice presentation. How can a large domain application be benchmarked upfront using different languages? Because they imagine we can't afford to rewrite the same app in several languages.
You can't? Come.
I can.
So benchmarks are interesting because you can achieve much of what you want to know from a very small benchmark, or what in the sort of the profession of people who like thrashing systems with heavy loads is called a micro benchmark. And this is really what these things are that we've built. They're small, realistic applications, micro benchmarks. And what you see when you benchmark something with a micro benchmark, so it might just be 2 or 3 very simple services that you need to build into your system when you deploy it, is when you build them with different languages, what you're seeing is really the effect mostly of how the deployment platform handles your language runtime. So one of the reasons Go is so much faster than Python is that the language runtime is really fast to spin up as the load scales. So Go is a very lightweight runtime compared to the others. And in reality, if you think about it, even if you get a request and you execute, I'd say a microsecond of business logic, what you're really doing is making calls to databases, you're making calls into the internal runtime of the language implementation. And the amount of time that your code runs for is typically a small fraction of the overall execution time to handle that request, because you're making calls into the runtime and language platforms. So you often don't have to do a great deal in terms of building complex benchmarks to see what difference the language will have. You could just build a small micro benchmark, deploy it, and measure the differences. And we found that really effective, and I think in general, that's exactly how people do this.
All right, thank you.
Shall I read it?
Please.
Okay, so another question. So there are a few questions that revolve around language comparison. So has C and C++ been tested on this, and how does it compare to Go? Because from their knowledge, Go has a similar philosophy for speed and efficiency as C++.
Yeah, we haven't actually deployed C or C++, I think because it's not supported by Google App Engine. I may be wrong, it may have changed, but I don't think it was last year anyway. There is a C#.NET support for Google App Engine, which we were trying to get to work, but we just didn't manage to do it in time. So C or C++ would be really interesting, but again, it depends on the runtime support that your platform gives you for that particular language. But I would imagine C or C++ would be fast. You'd hope so.
Yeah, it should. Also, speaking of different platforms and different languages, do you know how Go versus Java performance behaves on other cloud infrastructures such as AWS or Azure?
No, we haven't tested it. That's our next project is when we get our AWS funding to do that on Lambda. And I don't know if it's supported on Azure. I would guess not somehow. So we did have. I have another data point. I teach a graduate class in scalable distributed systems, and one of my students implemented their final project in Go, whereas most of the other people in the class implemented it in Java. And this was deploying Go on VMs on AWS, and it was incredibly fast compared to the performance we got from the Java implementations. There's a very fast runtime library for communications, handling HTTP traffic in Go, which made a considerable difference. And just the overall infrastructure was really lightweight and fast, even deployed on a medium-sized AWS VM. So I think, from performance standpoint, Go seems to be a really fast, efficient language.
Okay, thank you.
Guess it's my turn.
Yes.
What load testing application has been used to test the various scenarios? Any automatic solutions out there?
Yeah, we actually built our own. I built a Java load tester to deploy this specific load. You can use, there's a whole bunch of load testing applications, Load Runner, etc. And some of my students have started using those in the project recently. So yeah, I would just investigate that. Some are free, some you have to pay a pretty considerable amount of money for. But there's a whole range of technologies that you can use to build load testing applications. There's a little quirk in them that you've got to be careful with. Martin Kleppmann wrote a really nice, I think it's Martin wrote a really nice article on this a few years ago. It's about if your load tester is not generating load in a multi-threaded style, what it can do is it can generate a request, get very fast responses, but then one request might stall, and this actually, if it blocks for a second, will give you this false effect in terms of mean response time, because one request might take a long time, the rest have all taken very, very short times because they're fast. So when you calculate the mean, you think, oh, that's excellent. But in reality, one of your requests took like 6 seconds. And the long tail is the real killer on systems performance. You really want to have some sort of controlled bounds on your P99, your 99th percentile request latency. And if you're getting some that have got an extremely long tail, then this can really cause catastrophic effects in your system through cascading failures.
Or perhaps even using median and not means.
Yes, median's better. Means are kind of dangerous in scalability. I wouldn't look at them in any great detail.
Still me?
Right. No, fair. Oh, yeah, you wanted to say something. I'm being polite.
Yeah, the same thing actually.
All right. So we have somebody who's asking if we should generalize the experimentation lessons we get from simple experiments. If we should generalize them to the full applications, because maybe they don't apply to the conclusions gotten from simpler experiment don't apply to the whole applications, and we're misled.
Yeah, I mean, it's a good point. Benchmarks is lies, damn lies, and benchmarks, as we all know. And generalizing from a generic experiment like this to your own deployment is probably slightly dangerous. But hopefully the method that we've used shows how you could actually investigate these kind of issues in your own setting through sort of lightweight benchmarks, using a simple load tester to measure those benchmarks. And then when you deploy on the cloud, look at how you can investigate the parameter space through deploying different versions that you split traffic across using load splitting and measure those. And the key thing here is measurement is really powerful. If you want to save money and still achieve scalability, you really need to have insights into the performance of your system. You need to observe in detail how it's behaving, and then you can optimize. And because most of the time in a cloud platform, your code is part of the cost that you're paying, but you're running mostly platform code. Configuring the platform correctly is probably the most influential factor in your cost.
Yeah, makes sense. Thank you. Thank you for that.
And one diving into the security perspective. So on a cloud-based infrastructure, a DDoS attack could be extremely costly, not only for business, but also from the bill you're getting from you're going to get from your infrastructure. Any tips of protecting against it?
Yeah, DDoS, I mean, I'm not an expert in that area in security, to be honest. I know some people here in Seattle, they have deployments behind something called a service called Cloudflare is popular around here, which will actually, protect them from DDoS attacks. So I assume there's, complex infrastructures there that you can use to protect yourself from a DDoS attack and hence a horrible bill at the end of the month. But yeah, I've not really dug into that area, to be honest, sorry.
No, but I think I agree with you, because there's no point in reinventing the wheel. So there are systems that do precisely that. And for instance, we have used Cloudflare a lot, and I can actually say that a couple of times working on some banking products, it really saved our neck.
Yeah, I know a couple of services around here that it has done that for as well.
I think we have one more question. It's about basically creating bursts. Yeah. How should the burst behavior be mitigated? And if you have any tips for burst functions or containers for creating burst functions or containers, while at the same time controlling costs.
Yeah, bursts are always dangerous. So, for example, AWS Lambda has burst control built into it. It depends, if I remember correctly, it depends on which data center you deploy on. There is a built-in throttling mechanism to a Lambda service, whereby I can't remember the exact numbers, but whereby if the load suddenly grows by a particular amount, then Lambda will throttle your service deployments for 5 minutes, and then it allows the server deployment to grow slowly after that 5-minute period. Again, the details might be slightly wrong, but that's basically how it works. So Lambda has that built in, and the reason for that is that you're running on a shared infrastructure. And if suddenly, one day, for some reason, all the code that was deployed on that particular data center suddenly wanted to sort of expand infinitely, then the whole set of servers would collapse because there wouldn't be enough infrastructure around. So that's one way of doing it, but it's an insight into the general mechanism that you just basically, you can throttle the amount of traffic that comes through. So you can do this through an API gateway, for example. They have throttling mechanisms so that you can just control the amount of requests that go through your gateway, and if you exceed some maximum, that you're worried about because your system may not handle the requests efficiently, or you may pay too much money, you can just send back a HTTP 500 or so saying system not available right now. So throttling is the main way to sort of control or put a lid on the maximum amount of costs that you can be charged under a particular burst scenario.
Thank you. So basically, yeah, we need to pay attention, because otherwise, yeah, we might pay more than we expected. So always.
Yeah, I mean, I think the whole issue here is, you know, pay attention to the way you deploy your system, the way you build your system, because if you're not careful and you do see one of these tipping point events where suddenly your load grows unexpectedly, not only can it bring your system down, but you can also bring down your accounting people as well, because they're not very happy at the end of the month.
Right. Well, yeah, makes perfect sense. And thanks a lot, Jan. It was very insightful. And yeah, hope to see you next time.
Great. Thanks so much, Dan, Andrea. It was really a pleasure. Thanks, everyone.
See you.
Thank you.
Bye.